All right. Thanks for having me, and thanks for coming to my talk. Before I jump into talking about deserialization vulnerabilities, just say a couple of words about my not working. Mic's not working. There we go. All right. Thank you. So just a couple words about who I am. So I'm Ian Haken. I work at Netflix. I'm a senior security software engineer on a platform security team. Our team builds a lot of cool stuff to keep our ecosystem secure, and we've talked about a lot of the things we do. So Google us or find these links after the talk and check out all the cool stuff we work on. But let's focus on what we're here to talk about today, deserialization gadget chains. So I'm going to talk about what a deserialization vulnerability is for people in the room that don't know exactly what I'm talking about, and just so that we're all on the same page. And then I'm going to give you kind of a very brief history of deserialization vulnerabilities, because it's not a new topic by any means. But then I'm going to really deep dive into gadget chains. So I'm going to talk about what that is, what it means, how we find them, and ultimately a new tool that I built in order to find gadget chains, and how we use that at Netflix to help discover and remediate vulnerabilities in applications. So what is a deserialization vulnerability? So in object-oriented languages like Java, which is the language I'm going to be really talking about today, but most of this applies to any object-oriented language, so C# and PHP and what else. But in these languages, data is contained in classes, and classes contain code. This is like the idea of what object-oriented programming means. But this has a really fundamental implication, which is that if you control the data type that some of your code is operating on, then you're also controlling what code is running, because the code is associated with the data type. So why is that significant? So here's an example of kind of a classic deserialization vulnerability in Java. So there's some REST endpoint, and it converts the body of that request into an object input stream, and this is the JDK's built-in deserialization library. And then it reads an object out of that input stream, so it deserializes it, casts it to a user, and then outputs user.render, whatever that means. So the intent is probably that the user is some class like this that just has a name, and when you call render, it returns some data. So this is totally innocuous, sort of nothing bad really happens here. But where things can get dangerous is if you have some other class on your class path, like this thumbnail user, which extends user and has a different render method. In this case, it reads a file off the file system and outputs that as the render method. And that means that if you were to serialize a thumbnail user and send that to this endpoint, you would get any file off the disk returned back to you. And so this is what I mean when I say when you control the data type, you control what code is running. And fundamentally, that's what deserialization vulnerabilities are about. So why am I talking about deserialization? If you've been following this vulnerability class, this has been like super talked about since around 2016. But really, this is a vulnerability class that goes back way before that. So some of the first talks about it were back in 2006. Mark Schoenenfeld gave a talk at Black Hat where he kind of describes what some of these vulnerabilities look like in popular enterprise applications, and in particular application containers. But even though this was kind of first discovered back in 2006, it wasn't really popularized until 2015. And that was with Frohoff and Lawrence's talk at AppSecUSA, where they gave this talk on marshalling pickles, where they basically described that there's all these RCE gadget chains in popular open source libraries. So it's not just if you're running a particular application container, but if you are pulling in any of these libraries into your application, then you might be vulnerable and you might have code execution in your app. And so the year that followed, I've often heard people describe as the deserialization apocalypse, because just everyone realized that all of these applications were vulnerable because there were so many common libraries being pulled in that have these issues. So 2016 had dozens and dozens and dozens of talks that you can look up about Java deserialization issues. But one of my favorite ones from that year was by Luca at an OWASP meetup, and it's called Java Deserialization Vulnerabilities. And you can look that up later, but he just does a really good job of giving you kind of like an overview of what they are and how to figure out if you're vulnerable and what to do about it. But in the year that followed after that, in 2017, Munoz and Morosh gave this great talk at Black Hat about JSON attacks. So up until this point, everyone was really focused on the JDK's built-in serialization and deserialization library and how to build gadget chains and exploits using that. And what Munoz and Morosh did was do a really good survey of all these other serialization libraries and in languages beyond just Java, and identified when those are possibly vulnerable and what kind of attacks you can do against those libraries. So just because you're using JSON doesn't mean you're safe from these kind of attacks. If fundamentally, if whatever serialization scheme you're using allows you to control what data types are getting deserialized, then you're potentially vulnerable to one of these kinds of attacks. And so this does a really good job of just kind of identifying the fact that there's more libraries where this kind of attack can apply. But in case you think this is the last talk about deserialization, you probably haven't read the rest of this schedule because there's another one in about 90 minutes from now in the gold room. So hopefully that just highlights for you that this topic is not dead. Like deserialization vulnerabilities are still a thing that are present and that we're interested in. And hopefully by the end of this, I'll also convince you that they're getting more sophisticated. So it's something we really need to be paying attention to. So, all right, why are deserialization vulnerabilities so bad? If they were just what I described on that first slide, then they probably wouldn't be that interesting. It's not that often that you have some class that overrides another class where one has innocuous behavior but one's really dangerous. And the reason that they're so bad is that there's these things called magic methods that classes can implement in order to control how they get serialized and deserialized. And because they control how deserialization happens, they get invoked before the deserialization actually finishes. So this means that there is code that's going to get magically run depending on what class is in that payload. And it has nothing to do with what you're actually casting it to on the other end. So here's the REST endpoint from that first slide. And suppose for the sake of argument, there's this evil class on your class path, which implements one of these magic methods. So read object is one of them. And it just executes arbitrary code. Even though this evil class can't be cast to a user, that magic method gets invoked before the end of the read object method. So before it even tries to get cast to a user. So that means that it doesn't matter what you've actually implemented in your application. If there is some bad code that you're getting in from your class path through some kind of transitive dependency, then you can potentially build an exploit against that application. So what's the deal with magic methods? You might be thinking like, I've never implemented one of those. How common can they really be? And the answer is that they're actually extremely common because there's tons of classes in the JDK that actually implement these magic methods in order to control how they get serialized. And the main reason for that is so that they're actually, the serialized version is compatible between different JDK versions. But that means that since those classes implement some of these magic methods and those magic methods end up invoking other methods under the hoods, then there become a lot of other known entry points. So for example, when a hash map gets serialized, if it was using the default strategy, it would output a bunch of tables. It would be very dependent on the specific implementation of the hash map. But instead, what JDK does is it just writes out its key value pairs as a list. So just a list of key value pairs. And when it reads those back in, it calls this.put with the key and the value that it reads out. And so that means that it ends up calling hash code and equals on every object read out of the input stream. So if there's some class which implements dangerous behavior inside of hash code or inside of equals, then we know that there's a way to jump into that code through a magic method. And that's by just wrapping it in a hash map. So hash map is probably the best example because there's lots of gadget chains that are built using hash code or equals, but there's other stuff in the JDK, like a priority queue, which will reorder things after it reads them back in from the payload. So it's going to end up calling compare or compare to on all those objects it reads in. So, all right. How do you get from these matching methods to gadget chains? Gadget chains is, of course, what I'm really talking about today. So what is a gadget chain? So here's a really simplified version of what that magic method inside hashmap looks like. And this is kind of what I just described. It's just reading in key value pairs as a list out of the payload and calling put val on them. In particular, it has to call hash code on each of the keys that it reads in. So here's an example of a class that might exist on your class path that does something interesting when you call hash code on it. So this is out of the closure library. And inside of this class's hash code, it's got a function map, and it reads out the hash code function from that map and calls invoke on it. So if we can supply an interesting implementation of this iFunction interface that when you call invoke on it does something interesting, then when it gets wrapped in a hash map, you'll end up invoking that. So here's an example of a function that does something interesting. It just wraps two other functions and takes the output of one and passes it to another. So we can supply, as an attacker, sort of whatever implementations of F1 and F2 we want. So for F1, we might supply this constant value function, which just returns whatever value is. And as F2, we can supply this eval function, which will then execute whatever gets passed into it. So this is actually a real example of a gadget chain that I'm going to talk about more later, that exists in the closure library. So if you put all this into a payload, and here's an example of what a payload might look like in kind of a Jackson representation, it would look like this. So you just wrap all these things the way I've described, and when you send that, this value down here is going to get executed before the deserialization even finishes. So the really important takeaway when you start understanding gadget chains is that they have nothing to do with what code you've actually written in your application. The one I just described was a gadget chain exclusively built out of classes in the JDK and the closure library. So if you have some transitive dependency that's pulling in closure, but you don't actually use it itself, then you can still build this gadget chain and send it to your application. So what gadget chains are possible is completely influenced by the cumulative collection of all of your dependencies and all of your classes, and not necessarily just what code is around the vulnerable sites that you're potentially exploiting. So what deserialization libraries are potentially exploitable? So I mentioned that Munoz and Moreau did this great survey where they pointed out that all these other deserialization libraries are potentially vulnerable to these kinds of attacks. So there's obviously the JDK object input stream, which is the one that's received the most attention and that I'm going to use for most of these examples. But Xstream is another example that allows you to build some XML that specifies object types and has some of these matching methods. So all of these JSON libraries are also potentially exploitable. And some of them depend on exactly what configuration they're using. But you should totally read the Munoz and Moreau paper or watch their presentation to understand when you can build exploits against these libraries. But kind of the important thing to understand is the fact that there are all these different libraries that kind of deserialize payloads in different ways and have different magic methods and are capable of deserializing different classes. Exactly what gadget chains can be built kind of depends on which library you're actually targeting. And that's something important to keep in mind as I keep talking. So, all right, how do you find vulnerabilities? Well, finding a deserialization vulnerability isn't that different from finding a lot of other sort of web application issues. And fundamentally, it's a question of does untrusted input flow into one of the sinks, so one of these deserialization libraries. So, whether you're talking about the object input stream, the JDK deserializer, or Xstream or Jackson, if untrusted input gets into one of those, then you're potentially vulnerable. And honestly, I think that talk that's coming up in like an hour and a half is probably going to go into this a lot deeper. So I'm not going to talk about this too much. But what I'm really interested in is what do you do with your application if you discover that it is vulnerable to one of these issues? So how do you remediate deserialization vulnerability? Well, if you look at that talk I mentioned earlier that Luca gave, his response was, it's 2016. Like, there are better serialization options than this object input stream, and really any of these other sort of libraries that have these issues. I don't know what the last time is I programmed against an XML SOAP interface, but hopefully that's not something that people are doing for new applications. And I think if you have the option of using a better serialization strategy, then that is absolutely the right way to remediate this problem. But what happens if that's not a good option for you? So who recognizes the things that I just put up here? Anyone? Yeah, all right, a few people. So that guy on the left is the Netflix Wii disc that got sent out in 2010 that lets you play Netflix from your Wii. There is some client code that's stamped on that disc, which if you plug it in today and try to play Netflix with it, should still work. If you then have to change the serialization strategy of the IPC mechanism that client uses to talk to the Netflix servers, you're going to have a really bad time because you have to make sure that it's properly compatible with whatever serialization strategy that client code is using. Same story for the guy on the right. So that's the first generation Roku, which also came out around 2010. And there are still these clients out there. So what happens if there are clients that you literally cannot update? How do you change your serialization strategy? It's a really hard problem, and it might not always be an option to just say, all right, we're going to use something other than the object input stream. And even if you're not in this situation where you literally have CE devices that you can't change, changing the IPC mechanism between clients and servers is a really hard thing to do. It is really time consuming, and it's very brittle, and you have to go on a campaign to make sure all your clients get off the old version and get onto a new version. And so it's just a very costly thing to do. So you have to ask the question, is it worth the effort to remediate this vulnerability? Because maybe that vulnerability you discovered does actually exist. Maybe an attacker can control what classes are actually getting deserialized. But is there actually a gadget chain in there? Like maybe you've looked at the WISO serial project, maybe you know that like these versions of common collections had these gadget chains and you're not putting any of them in. So you're just like, I'm pretty sure you can't actually construct a gadget chain against my application. Should I spend like a quarter of efforts actually changing out what serialization strategy we use? So you want to be able to answer the question when you discover one of these, is my vulnerability actually exploitable? So how do you know if it's exploitable? How do you find exploits? So I just mentioned WISO Serial. This is one of the, I think, most well-known projects in this space. It's maintained by Frohoff, and it's basically a collection of gadget chains that researchers have discovered in a bunch of different open source libraries. So it's mostly focused on the JDK object input stream, but it gives you a really good way of just like surveying what things have known issues and making sure you're not using them. So MarshallSec is another research project that has wider breadth on different deserialization schemes and for different languages. But you know, again, it's mostly a list of known gadget chains. So neither of those projects is really going to give you a good answer about what about, you know, is there a gadget chain that uses the specific combination of libraries I have that utilize classes that are in multiple libraries? Or for that matter, what about a non-standard deserialization library that my application happens to be using that security researchers haven't spent a bunch of time staring at? So there's some existing tools beyond the ones I just mentioned that might help you do that. So I already talked about WISO Serial, and Frohoff even has this graph discovery tool for trying to find different method invocations that can potentially build up gadget chains. But there's some other tools like Jugal, which is a way to programmatically query about data types on your class path, which can kind of help you build up gadget chains one step at a time. If you're sort of doing it manually, it helps you with each step. And then there's some other like burp plugins like the Java Deserialization Scanner, which mostly use payloads from WISO Serial, and the NCC Group plugin, which came out earlier this year that mostly uses payloads from some Marocha's work. But kind of all of these things are basically still relying on like a bunch of known gadget chains and figuring out whether or not they can be used against your application. So since none of those things were really telling me about gadget chains specific to my application and specific to my deserialization library, as I was trying to answer this question of, can I attack this application with just kind of vulnerability, I wanted to build a tool that would solve this problem for me. So what I really want to evaluate if I'm building a new tool is the risk of a vulnerability. How important is it to remediate? And if that's your mindset, if you're not necessarily trying to build actual exploits, it kind of makes this problem a little bit easier. So if you want to evaluate risk, obviously the main question is you want to know if it's exploitable, but you kind of want to know specifically what exploits are possible. If a denial service is obviously different from an RCE. So you want to know what gadget chain can be built, not necessarily just do any exist. And you need to consider the entire class path. So not each library you're pulling in individually, but to your application as a whole. And as you're doing this, you can also make a bunch of simplifications, given that we're really just trying to evaluate the risk of a vulnerability. So for example, it doesn't need to be perfect. Some false positives are OK. The idea is that a human's going to look at this at the end of the day and decide how important is it to remediate this vulnerability. And also, and I think kind of most importantly, is that you're not looking for vulnerabilities with this tool. You're going to assume that through some means, through either some penetration, some other scanner, you found that there's a deserialization vulnerability, and now you're just trying to answer, can you exploit it? And also, you don't actually need to generate payloads if the goal of this tool is just to tell you, like, what is the riskiness of this vulnerability. And you probably actually could generate with the tool I'm going to describe, but that wasn't a goal that I was setting out to achieve on day one. So I tried to build a tool to do this, and I called it Gadget Inspector. And so what this tool is a Java bytecode analysis tool that will look at an entire class path and try to build gadget chains. And so in doing so, it's going to output what it thinks are the possible gadget chains that it's discovered. And then you, as an application security engineer or as a penetration tester, can use that as either a starting point to try and decide whether or not these exploits are actually possible and whether application can actually be exploited, or just as a way of saying, like, there's too many possibilities. I think we should fix this anyway, or maybe it outputs nothing, and you're like, all right, there's probably nothing here, and we can take our time with it. So what does Gadget Inspector do? So it operates on any given class path, so it can point to either a specific library or an entire war, and it reports the discovered gadget chains. The gadget chains are basically just a sequence of method invocations that it believes that it can jump to. And the way it does figures out those sequences is it does some simplistic symbolic execution to figure out whether there's data flow from arguments down into subsequent method invocations. And that sort of process is really just to rule out a bunch of false positives that crop up if you're doing this analysis naively, where if you just look at what methods get called, then you're not actually checking whether there's data flow from call to the next one. But most importantly is that there's a bunch of simplifying assumptions we can make in this process that actually make the code analysis very easy. And a lot of that's just due to the context we're working in. If you're thinking of the attacker as controlling this payload that you're reading in, so that they're able to control every field value on the object that you're operating on, then you can make assumptions about which branches you take in an if-else condition, because pretty much all the variables going into that if-else are going to be controlled by the attacker. So that's the kind of thing that I'm talking about, where you get to make a bunch of simplifying assumptions that normally make code analysis really hard. Normally, deciding if a branch condition is satisfiable is one of the hardest problems in code analysis. So you don't need a degree in code analysis to figure out what this tool is doing. So how does it kind of specifically work under the hood? So here's an example. So here's some known entry points that we will discover through just kind of enumerating the methods that are on our class path. So in this case, we know equals is an entry point using the trick of wrapping it in a hash map. And somewhere inside the equals method, we might call collection.contains. And in this case, we know the O that gets passed into equals is attacker controllable, as well as the this object that we're calling equals on. And that's because both of those things are basically read in by the hash map as key value pairs, and you're going to call equals on it. So what we're going to do is we're going to look at all implementations of contains that are on our class path. Because that's the thing. The O that we're calling contains on, we're assuming is attacker controllable. So any implementation of a collection could be used as the O that's getting passed in. So we're going to enumerate all implementations of contains and continue doing a graph search on each of those implementations. So here's one particular example, and when we jump into it, we're going to say that the this that gets passed in as the argument T we know could be attacker controllable, as well as the implicit this. And then if the implicit this is attacker controllable, then all the fields on it are, because that's, again, the entire object is something that's getting deserialized out of a payload. So we're going to look at all methods invoked in that one. And so there might be something like q.head. And basically, we're just going to continue this graph search on and on and on, always looking at all implementations of a class whenever we jump to a new implementation. And eventually, we might see that we get somewhere interesting, some piece of code that does something that has a side effect, like runtime.exec, or maybe something that reads or writes files from the disk. And whenever we see one of those, we're just going to output that as our gadget chain. And that's basically all there is to this. Devil is in the details, so for the sake of time, I'm not going to go through all of the ways that this thing does symbolic execution, but I've got a white paper up, as well as some, the source code that you can go look at and see exactly what this thing is doing. But that's the general idea. Basically, it's just a graph search through method invocations with some tricks to rule out some false positives. So the most important thing in what Gadget Inspector does, though, is that it allows some flexibility for the deserialization library that you're talking about. So in particular, there's lots of customizations that you can make around the idea of what's considered serializable. So I mentioned in that analysis that we were going to look at all implementations of collection.contains. That's a little bit broader than what I actually want to do, because I really want to look at all implementations inside classes that are considered serializable. So for the Java object input stream, only classes that implement the serializable interface can actually be shoved into a payload. But that's different for something like Xstream, where it depends on what converters have been enabled in your deserializer. Or for something like Jackson, only classes with a no-R constructor can actually be deserialized by Jackson. So exactly what classes you consider when you're looking at all implementations is something that's configurable. Similarly, what are the deserialization sources, what are the magic methods, are things that are going to differ depending on what library you're talking about. And also what method implementations you should consider is something that varies a lot between these different libraries. So again, for the object input stream, all implementations would work, but for Jackson, it really depends on exactly what annotations are on the classes. So you can be smart about how you're building up those call graphs and therefore what gadget chains you're actually looking at. So, all right, I built this tool. I claim that it does cool stuff. But obviously, until I actually run it on something, I don't actually know that it's doing useful things. So first thing I did was ran this tool on a bunch of open source libraries to see what it would come up with. So the very first thing it came up with was this gadget chain enclosure. And this is what I was alluding to in that example from the beginning of the talk. So the Commons Collection RCE gadget chain that Frohoff and Lawrence came up with in 2015 was super interesting because it was the 30th most popular library according to mavenrepository.com. Clojure is the 6th most popular library, so it's pulled in by even more things than Commons collections. But despite that, it has an RCE gadget chain in it. So this was super interesting to discover. So what this gadget chain does that it discovered is basically load an arbitrary file off the disk and execute it. It turns out you can tweak the last step in there a little bit to call eval instead of load script and basically get arbitrary code execution. So this was super cool to discover, and I reported it to the Clojure dev mailing list, and they basically just turned off serialization of this class in order to close out this gadget chain, because who's actually using serialization of this class? And they're like, no one, so we're just going to turn it off. So yay, all right, making the world a safer place. In scanning some of the most popular libraries, a bunch of stuff also popped up for Scala. Scala is really interesting because it's the 3rd most popular library. So I didn't find an RCE gadget chain in Scala, but I did find this gadget chain which would basically write or overwrite a file with 0 bytes, which is potentially interesting because you can basically denial of service a web application by overwriting some of its resources. Conceivably, you could also do something like zero out a blacklist, like an HD access file. So again, pretty interesting. By tweaking that a little bit, another gadget chain that I discovered in Scala allows you to do in SSRF, do a get against an arbitrary URL, which if you've ever done any pen tests against applications, usually once you manage to do some kind of get operation inside the perimeter, you can end up doing a lot of interesting stuff. So also super interesting. But in rerunning Gadget Inspector sort of shortly before this talk to see like what it might have missed due to kind of some improvements I made in the meantime, it discovered a new gadget chain inside Clojure that uses a different hash code entry point and comes up with exactly the same gadget chain that I saw the first time. So even though the Clojure community patched that RCE gadget chain that I found before, there's still a new one in every version released since. So if you're pulling in any version of Clojure and you're doing unsafe deserialization, then there's an RCE vulnerability in your application. So you should check that out. But OK, obviously the whole point of this talk is to talk about how we can use this tool to more effectively remediate vulnerabilities discovered in applications. So what I wanted to use this tool for at the end of the day is to scan applications at Netflix and figure out whether or not we need to remediate vulnerabilities we found. So here's one example of an internal web app where we discovered a deserialization vulnerability. So this was using Jackson, and an attacker could specify an arbitrary class to deserialize and specifies the whole payload that Jackson's going to deserialize. But because it's Jackson, it's got some limitations. So it can only deserialize class with no arg constructors, and its only entry points are going to be set methods. Now, that doesn't sound too interesting. Usually setters are kind of no-ops that don't do anything interesting. But that does include methods named setup or similarly. So there might be something there. And in particular, this app had like a 200 megabyte class path. So it had like literally thousands and thousands of classes. So there might be something interesting there, even though it's kind of hard to conceive of a good gadget chain subject to these restrictions. So ran Gadget Inspector, and it didn't come up with anything. It came up with like 2 false positives that were easy to rule out. So we're like, all right, we're going to take our time fixing this. It's not the biggest deal in the world. We don't have to drop features for the quarter in order to like work on this right away. But I'm not going to leave you with that. The next one that I was using this for used some really interesting non-standard deserialization libraries. So we had a penetration test team looking at this application, and they discovered that it used this non-standard deserialization library, and it was doing unsafe deserialization with it. But because it was this sort of weird library, it had a lot of really weird, unique constraints on it. So it still had a magic method. It would use read resolve, but not read object, which is the one that the object input stream usually uses. But serialized objects don't need to implement serializable, which means that you actually have almost every class and every class path to work with. But there's a bunch of other weird restrictions on it. So member fields of the serialized object can't have a $sign in them, for example. And that's just because of the way that it was actually encoded in the payloads. Like it would just break the encoding scheme. There was no serialization support for arrays or generic maps. And most importantly, it didn't let you have any null values for fields on objects. And that means that there was this recursive requirement where every field also had to satisfy all these requirements. So it was really, really hard to even say what classes on the class path could be deserialized. But that's the sort of thing that you can just kind of configure inside Gadget Inspector and run it on, and this is what it came up with. So this is some crazy 12-step deep deserialization gadget chain, and this was a real gadget chain. This was a true hit. And I'm not going to make you like read every one of these lines or go through exactly what this means, because that would take a half an hour by itself. But if you just kind of let your eyes fuzz a little bit and look at the different package names here, there are 7 different libraries involved in building this gadget chain. And like that includes the JRE and the application itself, not just libraries that it's pulling in. So this is something that the penetration team, even though they spent a couple days looking at this app, did not find by themselves, and with good reason. I don't know how long it would have taken me to find this manually. But what this thing did was it allowed you to copy an arbitrary file from some input path to some output path. So this basically allowed you to exfiltrate private keys out of the application. But with a small tweak of the last step in this, you could actually write an arbitrary string to an arbitrary output path, and in particular write a JSP out for the application and get RCE. So with about 30 minutes of effort, I was able to discover that this vulnerability led to RCE using this tool. So that was something that we wanted to remediate right away. So this tool is basically a proof of concept. We've been using it for a little while now at Netflix, but there's lots of rooms for improvement. It really doesn't handle reflection too well. It makes a bunch of assumptions that could be improved that are currently being false positives. It only knows about entry points using known tricks, and in particular, it only knows about sinks with interesting behavior based on a list of known sinks. So there's lots of ways this thing could be improved. I'm not going to tell you that like you run it and you know whether or not your app is safe. But it definitely has started saving us a lot of time in remediating these kind of vulnerabilities. So automated discovery for gadget chains, I think, is new territory. This is a functional prototype. There's lots of rooms for improvement, and it's specifically written against Java applications, but I think all these ideas apply just as well to other languages like C#. And this thing is open source, so I encourage people to go check it out, look at the source code to understand how it works, see if you want to apply it in other contexts, or just improve it, make it understand other deserialization libraries. And most importantly of all, I think I want you guys to walk away with the message that deserialization vulnerabilities aren't going away yet. We keep finding them and we keep talking about them, and exploits are getting way more sophisticated. So I think we need some better tools to understand them as well. So that's all I've got. Thank you all for coming.